In this presentation, I'm going to go over some of the more advanced things that you can do with our AJA Orion sputter systems in terms of layer and process creation. First, let's just review what would be sort of the simplest sputtering process that you could come up with. And that would be a single gun being used to deposit a single film without any changing conditions during the deposition or any additional layers with different conditions. To do this, we'd start off by building a layer where we are going to ignite our plasma, and this would be the first layer. A plasma ignition process is pretty simple to start. We start off by setting our process pressure and our gas flow, and then after that we will enable our gun power so that we're actually applying power to the target, and then this should strike our plasma. We wait for our plasma to ignite, and then we give it a little time to stabilize. After that, we're going to actually ramp our process conditions into the parameter space that is going to be more ideal for the layer we want to deposit. We would reduce our pressure, adjust our flow levels to suit. Then we would gradually ramp our gun power to the desired power, whatever that is. And then after that, we might do an optional pre-sputter. This is basically where we allow the target to be sputtered in the process conditions for a few minutes prior to opening the shutter. What this allows us to do is clean the target surface of any reacted compounds and debris that might be there from previous processes. After that, we're actually going to begin the deposition itself. We would open the shutter on the gun, and now the material flux from the target is approaching the substrate. The deposition is then occurring. Once we've deposited as much as we like, we close the shutter, ramp down the gun power, turn off all the gas flows, and then we are done. Let's take a look at this in a way that shows us how parameters might be set and change over time. First, let's take a look at our striking layer. We would set our desired pressure, something like 30 millitorr, and then we would set the gas flow rate, also something like 30 SCCM. We would apply a small amount of power to the target, therefore to strike the plasma, and then we wait a little bit of time for the plasma to stabilize. Then we would enter our deposition layer, and in the deposition layer we would immediately drop our flow rate, we would drop our process pressure, then we would gradually ramp the power up on the gun. At this point, we would begin what would be called our shutter delay phase. After that's over, we would open our shutter, leave the shutter open for whatever the designated coating time is, then close the shutter and ramp the power down. Once the power is ramped all the way down, we can turn the gun off, and that's the end of the process. So let's take a look at the actual layer creation screen where we build these things. First, we're going to look at the strike layer itself. So I'll just kind of go over what some of these controls do again in a later slide, but for right now, just follow along. We've set a rotation speed of 10 RPMs. We've put our pressure control into pressure control mode. That means we want it to control the pressure specifically. You can also put it in position mode, where you say hold the valve at a position between all the way opened and all the way closed, and it can reside at any one of 1,000 increments between those two extremes. But for most purposes, you're going to end up using this pressure mode. 30 millitorr is a good striking power, good striking pressure. We have opened our argon flow to the gun we're going to use. We have turned the argon flow on from our mass flow controls, and we've set the flow to 30. We've enabled the power on our gun, which is connected to gun 1. It has a 2-inch titanium target in it, and it's powered by DC5. That is the power supply that it is connected to this. It's enabled. We're operating it in watts mode, meaning that it's going to control the power and adjust the voltage and current as necessary to maintain that power. We've set our power to 30 watts to strike it. Now we also have this set here into arc detect mode. This is something I'll talk about later when we talk about the pulsing We do not have a shutter delay because we're not going to be opening the shutter. We have not enabled the shutter because that would open the shutter. And we've set a coat time of 10 seconds just to let it stabilize. We are not going to do this shutter carryover. This is when you want the shutter to stay open as it moves into the next layer, because we haven't even opened the shutter at all. And lastly, we've set the idle power set point. What this does is it says, hey, after you've done all this stuff, leave the power at 30 watts. This is super important. If you don't set this to 30, or if you leave it at 0, when this layer ends, it will turn the power supply off. If the power supply goes off for even a brief moment, you will lose the power. Moving into our next layer, we're maintaining the rotation speed. We've dropped our pressure down to 3 millitorr. We still have the same valve open to the argon tubes. We've stepped our flow down to 20 SCCM. Now what we've done is we've set a ramp time of 80 seconds, a power set point of 150 watts, so it's going to ramp from the previous value in the last layer, which was 30 watts, up to 150 watts, and it's going to take 80 seconds to do that. So you don't set the slope, you set how long you want it to take and where it's going to. Once it reaches that set point, now it will begin to count through the shutter delay, which I've set to 60 seconds. Once the 60 seconds are up, it will open the shutter. It will keep the shutter open for 200 seconds. This is when it will actually be coating the substrate. Once those 200 seconds are up, it will close it. And then it will ramp back down to this idle set point, which is 30 watts. It will do so over a time period of 80 seconds. One thing that's kind of important to know about the relationship between this ramping up and down is that if your ramp time is, whatever time, say 80 seconds, and your power set point was, let's say 150, if your idle power were 149, it will ramp from 150 to 149 over 80 seconds. So it doesn't actually care what the difference in power settings are. It just knows there's a difference in power, and here is the amount of ramp time I'm supposed to use to go from one power to the next power. The last thing I'll mention briefly is this sub-Z height set point. This is something that you can optionally set if you like. You generally want to make sure that it's set to 0 if you're going to set it manually before you start the process. But if you want to make sure that your processes are consistent and that they're always going to the same height, you can set this to 0.75, and that will be the best uniform height for all of the guns in the system. So now that we've taken a look at what those layer processes look like, we're going to just revisit this detailed breakdown of how these power supply parameters work. Some of them have a DC switch. This is basically a switch box that allows us to take the cable from one power supply and split it to multiple guns. This does not allow you to operate multiple guns simultaneously from the same power supply. All it allows you to do is power one, then power another one, then power another one. You would use this in an automated fashion where you would strike a gun, ramp it up, do your deposition, ramp it back down, turn it off, then change the switch position to a different gun, and then repeat. So that way you wouldn't have to actually stop in the middle of your process and swap cables manually. You can just tell the software to swap where you want the cable to go, so long as it's connected to the right guns. Then there's this delay time. This is something we didn't use in the last example. The delay time is going to take effect prior to beginning the ramp. You can use this in a layer to create offsets between what one gun does and what another gun does. We'll give an example of this later on. Then there's our ramp up and down time in seconds. This will ramp up or down to or from our power set point. You can then, if you're using a DC supply, change the power mode. You can operate a DC supply in constant power, which is watts mode, constant voltage, or constant current. And the difference between all these modes is that whichever one you set, it's going to adjust how much current it needs to force through or how much voltage it needs to use in order to maintain a constant for whichever one you set. Because we have it in watts mode, if we put a set point of whatever, 30, that means we're setting 30 watts, and it will adjust the voltage and current as necessary to make sure that we stay as close to 30 watts as possible. So this is that current set point. It doesn't have units because the units of it depend on what you have this set as. Then there's this pulse frequency and pause duration. These settings only take effect if I've got this drop-down selected to pulsed mode. When you have arc detect selected, it behaves like a normal DC power supply, and that it just has a constant power output. After we reach our set point, we would have a shutter delay. It counts this number of seconds before moving on to shutter enable should you choose to open the shutter. Enabled means that it's open. Then it would count through a coat time. This is, our deposition time. After that, the shutter carryover would take effect. If you set it to closed, it will close the shutter. If you set it to open, it will leave the shutter open, assuming the shutter was open previously, to move into the next layer. So if you have this open and you have a ramp time and it's going to be ramping to a different idle power set point, it will leave the shutter open while it does the ramp down to the idle set point. So the next thing that we're going to take a look at is when we want to add substrate heating to a process. The first thing you need to know is that rotation must be enabled in order to use the heat. You could have it going as low as 1 RPM, but I would probably do it a little bit more for better uniformity. Once that's enabled, we can enable the substrate heat. The settings that we have for substrate heat are this temp ramp. We can set a ramp rate if we like. If we don't set a ramp rate, it'll ramp about as fast as it can, which is about 1 or 2 Celsius per second. But you could make it go slower if you wish. Here you can set the desired temperature. So in this example, I've set it to 500 C. It shows you it's got a maximum of 800 C. Once it reaches the set point, then you can set a soak time. And the soak time will basically just keep it at this temperature and count through this amount of time once the set point is reached. Shutter enable doesn't do anything because we don't have a substrate shutter. I've got pressure control set to open. This is something that I might do if I want to outgas a sample. I want to just leave the chamber as, pumping with as low pressure as possible and outgas as much as I can from the substrate and pump it away. However, I could also set a pressure and I could flow gases and I could soak my heated substrate in an environment that's saturated with oxygen or nitrogen, let's say. So I'm going to walk you through an example of a heated molybdenum deposition, and it's got 3 parts to it. The first part is where I'm going to do a preheat. I've set my rotation. I am leaving the main valve open so that I'm leaving it at high vacuum. I've set my substrate heat to 500, and I've got a soak time of 30 minutes. It will ramp up as fast as possible to 500 C. It'll stay there for 30 minutes, all the while with the main valve to the turbo pump open and pumping out any gas that evolves out from the substrate. The next thing I'm doing is I am going to strike my layer. So I've strike my gun. So I've set the pressure to 30 millitorr. And I still have the heat enabled. I don't have any soak time anymore because I'm already at 500 and I just did my soak in the last layer. I've chosen to flow the argon to the center gun, which is gun 8. And I've enabled my argon and I'm flowing 30 SCCMs. I have also set or enabled the power to RF4, which is connected to gun 6. And it has a 2-inch molybdenum target in it. Just like any other striking layer, this stuff is not changed by the fact that I added heat. 30 watts to strike it, no shutter delay, no opening of the shutter, a little bit of coat time to let it stabilize, and then I'm leaving the idle set point where it is. Oh, note in this layer I have also put the substrate height to 0.75. That way I know it went there at the start of this layer and should stay there for the rest of the process unless I instruct it to go elsewhere in subsequent layers. Okay, so I've still got the heat on. This is the third layer. 500 C, no soak time. I've set my pressure down to 3 millitorr. I've stepped my flow down to 20 SCCM. I've set a ramp time of 60 seconds to ramp up to 130 watts. Once it gets there, it'll do a shutter delay of 60 seconds. Then it will open the shutter. Then it will coat for 60 seconds. Then close the shutter and then ramp back down to 30 watts over a period of 60 seconds. So let's look at that complete process in this sort of graphical way. My entire process is consisting of 3 layers: a substrate preheating layer, a layer where I strike my gun, and then a layer where I do my actual deposition on the heated substrate. The first part of my preheat layer is a temperature ramp. I ramp my heat up to a desired value, and then I set a soak time, so I soak for a while. Then, leaving it at that temperature, I begin setting up for my strike. I set my process pressure, I set my gas flow, I put a little power on the target to ignite it. Once it stabilizes, I move into the third layer. During the third layer, I drop my process pressure down, I drop my argon gas flow down. It's still 500 C throughout the entire layer. And at the beginning of the deposition layer, I start to ramp the power on my gun up. Once I get there, I go through my shutter delay, then I open the shutter, then I go through my coat time, then I close the shutter, then I ramp down. And if this is the end of the process and I've had it instructed to stay at 500 C the whole time, then as soon as it says process complete, it'll immediately cut the power to the heating lamps, and the heating lamp will it'll just cool down naturally on its own. The next thing we're going to talk about adding is substrate plasma cleaning or ion bombardment during growth or before growth. This RF1 supply, you'll see that it just says bias and it doesn't have a target listed. That's because it's connected to the substrate, and this is a way that we can do things like pre-clean or even an etch, though it's kind of a gentle etch to materials and substrates, and we can even apply plasma to the substrate while we're depositing a film and do what's called ion-assisted deposition or ion bombardment, as I previously called it. You can use this method to modify film properties, modify strain, modify surface morphology and crystal structure. You can use it to promote adhesion, and you can use it to probably do a number of things that I'm not aware of. So basically all you have to do is operate this like any other gun, and you could operate it at the same time as you operate other guns. So we're striking it just like we would a gun. I've set rotation. I generally just set rotation to 10 as a default unless I have a reason to do higher or lower. I've set my pressure to 30 millitorr. I'm flowing my argon to gun 8 again. I've got argon flowing 30 SCCMs, and I'm enabling this 30 watts just like I'm striking a target. Shutter doesn't do anything because there's no substrate shutter. I've got a coat time to let it stabilize. This, of course, doesn't do anything. There's no shutter. And then I'm leaving it at 30 watts to go into the next layer. So one thing I'll mention about this is a kind of rule that I established in my general training presentation is I've got some ramp rates that you should use for different targets and different materials. You can treat this like you're using a metal target, even if your substrate is not a metal. That's because the power density is pretty low. It only goes up to 100 watts, and that 100 watts is distributed across the whole sample holder, which is greater than 6 inches. So it's a pretty low plasma density overall, and you don't really have to worry too much about stress or strain from sudden thermal changes and fracturing your substrate. So as a result, you can ramp it like you would a metal. You can do a change of 100 watts per 60 seconds. And you could even strike as high as about 50 watts. In some circumstances, I'll actually strike higher than that. I don't really do that too often. I don't like to turn the power supply on right at its max power, But if you really need to do it, I don't think you will damage anything if it's not done excessively. So what we're going to do is we're going to take a look at a process where we add ion bombardment as a pre-clean. First layer that we had done or had shown before was just a snip of this where I had struck this as if it were a gun. So now this would be the second layer where I've turned my pressure down to 3, I've turned my flow down, and now what I've done is I am ramping up from my 30 watts that I struck at to 100 watts, and then I'm going to let it stay there for 60 seconds and then bring the power back down to 30 over 40 seconds. So this would be something like I'm using it like a pre-clean in this example. Why do I come down to 3 watts? Well, it's a pretty good stable space for sputtering, and that's basically what we're doing. We're sputtering the substrate as if it were a target, and that's really all there is to it. So what does this look like if we add something like that to the beginning of a deposition layer? So if we kind of look from like a top-down sort of way, we've got our complete process, which consists of a substrate clean and a deposition sub-process. In our substrate cleaning process, we've got 2 layers. We've got a strike and a clean layer. Those were the 2 examples I had just shown. You strike it like you would any other gun. You've got a process pressure and a flow. You apply the power, then you drop your flow, you drop your pressure, you ramp it up. Now your coat time is really where you're doing the bulk of your surface pre-cleaning or surface modification, and then you would ramp it back down if you desire. You could also leave it that way into the rest of the deposition process if you wanted to. Then we're entering the deposition side, where we would start with our strike layer, you know how that works, and then moving into our deposition layer. So all we've done is we've just tacked this on to the beginning as a way to pre-clean the substrate. The next thing I'll start to move into is talking about reactive sputtering, and that is making oxides or nitrides or even oxynitrides from pure metal targets. This is something that I cover a little bit in one of my other presentations, so I'll just kind of go over it pretty briefly. This is an example of a sputter gun on the bottom and our substrate on the top, and we've got a metal target, which is this orange color. And then we've got something like our metal oxide or metal nitride that is forming on the surface. Well, why is it forming on the surface? Because we've decided to flow in a reactive process gas such as oxygen or nitrogen, and we've decided to flow it in at an entry point that directs it at the substrate. At the same time, we are flowing argon gas in through an entry point that actually spits it out right at the target surface. And so what this allows us to do is have a higher partial pressure of our reactive gas near the surface of the substrate than we do at the target surface. Now this is optional. You could also, in some configurations, flow both gases directly to the target surface. This can be useful when you're making nitrides. Nitrides are, when you're trying to make a metal nitride, the nitrogen itself is not as reactive as oxygen, and so it helps to activate that nitrogen in plasma phase. And so by combining them here where you have a high plasma density, you can make that nitrogen very reactive, form the nitride directly on the surface, and then ablate it off, or even form it in flight as metal atoms are moving through this energetic region. You can also apply plasma to the surface. You can strike with RF1 and you can have a plasma at the surface to facilitate reactions like that at the surface if you want to keep the target surface free of the reacted material. So we're going to talk about some examples where we do reactive sputtering next. So we're going to look at an example of making reactively sputtered tin oxide, and this is a 4-layer process. We start off as you might expect. We are going to use some substrate heating, so we set our rotation, we set our pressure to 30, and we're just flowing argon, gun 8. Substrate heat is on. We're heating right up to 500, but we're not going to do a soak. We're just going to heat up to 500, and as soon as it hits that, we'll move into the next layer. And in this same layer, what we're going to do is strike our tin. So we've enabled it. 20 watts. I use a little bit lower power for tin because we don't really want to go much higher than 30 watts with tin. And then I just have a coat time of 15 seconds, which is pretty irrelevant because it's going to stay there for a while. And then idle set point of 20. What will happen is all this stuff will happen on this side, and then this stuff will happen. So it'll set the pressure, it'll set the heat ramping up to 500, it will open this valve, set the flow, strike this, and then it'll just sit running at 20 watts while this ramps up to 500. As soon as it reaches that, it'll move into the next layer. So now in the second layer, I'm still at 500 degrees. I've moved my pressure down to 3 millitorr. I've stepped my flow down to 20, and now I've introduced oxygen flow at 2 SCCM. In this example, I'm not actually going to change the power that I'm applying to the target. You could if you like. All I'm going to do is let it sputter with the substrate shutter, with the target shutter closed for about 300 seconds. This is a method you can use if you are doing reactive sputtering, where the goal is to get the rate of reaction or the rate at which reacted species are covering the surface and leaving the surface, or forming on the surface and leaving the surface of the target, to allow it to equilibrate. You'll see this in a lot of papers where people do longer pre-sputters when they're doing reactive processes so that this type of thing occurs. 5 minutes is pretty effective. You may see 10, 15, but you won't see people do it for hours. They do it for a few minutes. Then I've opened the shutter, I sputter for a while, I close the shutter, and I don't need to do any ramping, so I'll just leave it at 20. Moving into the next layer, what I'll first point out is that I've now turned the power supply for tin off. So I'm no longer sputtering tin anymore. The tin oxide has already been deposited on the surface, or at least what I hope is SnO2. Now what I've done is I've increased the pressure up to 80 millitorr. I've left my temperature at 500 Celsius. I have turned off all the valves for argon and nitrogen, and I've just got oxygen flowing, and I've got a lot of oxygen flowing. I also have a soak time of 5 minutes. So what I'm doing here is I'm increasing the pressure quite a bit. I'm leaving it at 500 degrees for 5 minutes, and during that time, I'm filling the chamber up with a lot of oxygen. This is like I'm trying to soak the film, the heated film, in an abundance of oxygen to try and heal or anneal oxygen vacancies or defects. And in the last layer, I'm keeping my pressure high, I'm keeping my oxygen flowing the whole time, and I've instructed it to ramp the substrate temperature down to 30 degrees. I've also set a soak time of 5 minutes. This is so that when it gets down to 30 degrees, it will wait 5 minutes before saying, hey, this layer is done. Now this would be the last layer in the entire process. Let's look at that graphically. Our whole process is made up of a deposition section and then this post-anneal section. The deposition section consists of a substrate preheat and a striking layer. We ramp up our temperature, we do our strike, we strike our target, then we move into the deposition layer, we drop our flow, we introduce oxygen flow, a small amount, and we drop our total process pressure. At the same time, we begin ramping the power on the gun. We go through our shutter delay, we open our shutter, we do the coating, we close the shutter, we ramp back down. Once we ramp down, we've cut the power, so the layers after this don't have any power to the target surface. We immediately knock this all the way up here, our process pressure. We increase our oxygen flow quite a bit, and then we have our heated oxygen soaking. At the end of that period, we allow the cool down to begin. we tell it to go down to 30, we leave the oxygen flowing the whole time, and we leave the high process pressure. And then once it gets down there, it's got a soak time for a while to let everything chill out and equilibrate. And then after that, we would turn off the oxygen flow and our process would be complete. So the next part of this presentation, I'm going to talk about this button you have on the process creation screen. On the process creation screen, you have this import Excel button. This is useful when you want to make very many layered processes, like if you're going to make something like 10, 20, 30 layers for a process, even up to 1,000 layers you can do. It's much easier to do it with our Excel sheet. Another reason why you might want to use it is if you're going to have a many layered process where there's very many small parameter changes per layer, such as you want to increment the power on the gun by 10 watts, deposit a few nanometers, and then increment another 10 watts, deposit a few more nanometers, and so on, something like that. It will make it much easier than doing it layer by layer in the layer creation screen. And also, anytime you want to view all the layers in a process at once, it's easy because they're all stacked up in an Excel file. So that's what we're going to cover in part 2 of this presentation. Thanks for watching. Have questions? Email me.